Hi, this is Mrs. Anderson, and I'd like to do the bouncing ball problem for you because you'll be doing this in class on Monday, and this way it'll give you a little head start. It's kind of a cool problem. It's a real world situation that involves a geometric infinite sum. So let's see. The problem is going to be that we're going to take a ball and drop it 10 feet. So if we drop this ball 10 feet, we know the first vertical distance would be 10 feet. Okay, that's what we're finding is the vertical distance. Vertical distance means the distance going up and down, not necessarily the total distance. Okay, so going back to the story, we're going to say that this ball bounces a half of the way up from the previous bounce. So it's going to be half the distance it was previously. So the next bounce would be 5 feet. And then the next bounce would be half of that, which would be 2.5. And the next bounce from that would be 1.25. And so forth. Now, in a pretend world, this ball would just keep going forever and ever and ever and ever because it would never get to zero. And I tried explaining to you in class about an infinite geometric sum that has a ratio of a fraction. It just keeps going forever, and the entries in the sequence just get smaller and smaller and smaller. So what we want to do is add up the vertical distance forever as this keeps bouncing half the distance it was before. So let's take a look at this. If we write it out as a sequence, it sort of looks like this. You've got 10, and then, well, we're adding, so say plus 5, plus 2.5, plus 1.25, and then it just keeps going forever. Sometimes it's easier to look at as at using fractions. So I'm going to rewrite it. I'll do it down here. Is 10 plus 5 plus 5 halves plus 5 fourths, and so on. So this is a geometric series because we're multiplying the previous term by half to get the next term. Oh, so if we know that, we learned that the explicit formula can be written as the first term, which was 10, times the common ratio, all raised to the n minus 1. So this formula for this particular situation is right here. But what do we want to do with it? We want to add it up. So how do we show that we want to add that? Well, let's just use the summation notation. So I want to start at the first term, but I want to go forever. So I'm going to infinity, and I'm going to put my explicit formula next to my e. Now, there's a couple ways we did this. We could do this on the calculator if you want, or we saw that it's really pretty easy to find the infinite sum and it does converge because the ratio is a fraction. So all we have to do to find the infinite sum is to take the first term and divide it by 1 minus the common ratio. Okay, so if I bring that, I'll just come right over here with this. So I can say that 10 over 1 all over 1 half, because 1 minus 1 half is 1 half, turns out to be 10 over, oops, sorry, that's a 10. 10 over 1 times 2, which is 20. So I could say, oh, this ball has traveled vertical distance 20 feet. But there's a little problem with this. Because, and I don't know if any of you are catching this, the ball is going up. Oops, sorry. The ball is going up, but it's also coming down. So each time it goes up, it's going to come down. So it's not only traveling 20 feet, it's doing that twice. So what I'm going to do is take that 20 and I'm going to multiply it times 2. So now that gives us 40 feet. Okay, so hopefully everybody can understand that. So this geometric sequence is really happening twice. It's going up and then it's coming down. Now there's one little thing wrong with that answer. the very, very first term, the ball is just going down. It's not going up and down. So what do we have to do to this 40 feet? We have to subtract that extra 10 feet that was included when we doubled the original sequence. So 40 feet minus 10 feet, then give us 30 feet. So the total vertical distance that this ball travels would be 30 feet. And so this is a nice example of how we can use a geometric infinite sum to answer the question of a bouncing ball. Thank you for listening, and hopefully this will help you do the problem that you have to do Monday in class. Thank you. Bye.